Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So we are very happy to have Ohad Shamir here from the Hebrew University. And he is going to be talking about when quantity makes quality, learning with information constraints.
Okay, thanks Jennifer for the introduction. So the topic of my talk is going to be learning with information constraints, and it's based on a few recent joint works with Nicolo Cesa-Bianchi and Shai Shalev-Shwartz. So I'll begin by recalling the standard model of supervised learning. So in the standard model, we assume that we have some unknown distribution over examples x, y, where x is some instance and y is some target value. And our goal is to find the predictor which, given examples drawn from this unknown distribution, is able to predict y well based on x. In the standard model, we also assume that to achieve this goal, the learning algorithm has access to some training sample, x1, y1 to x and ym, drawn independently from D. In this talk, I'm going to discuss a somewhat different setting where the learning algorithm has only partial information on each training example. This is not a completely new setting. There have been previous works which fall under this framework, but we take it into various new directions which haven't been considered before. Specifically, I'm going to discuss three settings: missing values, noise with unknown distribution, and learning with privacy preservation. And I'll explain each of those in much more detail later on. But I'd just like to point out the main message or common theme of my talk, which is showing how it's possible to construct algorithms which, by getting more examples, are able to fully make up for the fact that you have less information on any particular example. And this holds both in the sense that with enough examples, it's okay to have arbitrarily little information on each specific example, and also that the algorithms I'm going to discuss come with formal guarantees. So if you give them enough examples, they are provably competitive with algorithms which enjoy full access to the training data. So starting with the first setting, so the first part of my talk is just going to be this informal motivation to the settings. So starting with missing values, so suppose you're a medical researcher and you want to characterize what makes people prone to cancer based on many possible attributes. So it can be age, sex, blood pressure, genetic profile, and so on. Smoking, obviously. So the standard way to go about it is to take a large group of volunteers who are willing to participate in your study, measure all these different attributes on each of them, and a few years later do a follow-up study to see who developed cancer, and use this to try and characterize cancer-prone individuals. So this usually works, but suppose you want to do a really large-scale study. You really have several dozen attributes that you want to measure on each person. So you go and publish this wanted ad, and for some reason, not a lot of people show up. So the problem, of course, is that most people don't want to spend an entire weekend in hospital and getting all their blood sucked away from them for the greater good of science. They're willing to spend, maybe 1 hour, maybe getting pricked with a needle once, but not much more. So this motivates a setting which can be denoted as attribute-efficient learning. So it's a setting where you can get a lot of examples, but from each example you can see only a few attributes. You can only do a small number of medical tests. So this was first proposed by Ben David and Dichterman. However, they focused on, yes?
I don't understand what the formal characterization of this could possibly be. I mean, you could say that full information is that y is included in x.
Well, because eventually you will want to find, say, a predictor which depends on all the attributes, not just on the 3 tests you can do on each particular one. But I'll describe the setting much more formally later on. Right now it's just an informal discussion of them. Okay, so the setting was proposed by Ben David and Dichterman. However, they focused on very specific kinds of predictors, such as KDNF formulas, which are different than the ones I'm going to discuss. There's also quite some interest in this setting in the data mining community, where it's called budgeted learning. However, the algorithms proposed there are mostly heuristics. They don't come with any formal guarantees how well they do compared to algorithms which enjoy full access to all the data. And I'm going to show you algorithms which allow you, by taking more participants, it's okay that you will collect fewer attributes from each one and still learn as if you had all the attributes and you can do all the medical tests you want on each person. Okay, the second setting I'm going to discuss is where you have noise. So the idea is that you have the real data out there, but you cannot really see it. Instead, you can only see a few noisy copies of the data. And moreover, you cannot even characterize precisely the noise distribution. So this is a very common problem in just about any data which is, say, gathered by physical measurements. So continuing with the medical theme, just for fun, consider medical imaging. So some medical imaging techniques are in fact not very healthy for you. For instance, in CT scans, what you do is you take many different X-ray scans of an individual from many different angles and use it to reconstruct some three-dimensional image of what's going inside. However, that exposes the individual to quite a lot of radiation, and there's at least some interest in the relevant literature on what's called low-dose CT, where you either take less scans or use less radiation, and it can work, but the result is usually a very noisy image. So thinking back on the medical study example, suppose you also want to do a CT scan, but maybe you can get a lot more people to participate in your study if you do a low-dose CT, because it's healthier, maybe it's also cheaper, it takes less time. So such a thing might be desirable, but then you have to deal with data which is noisy. And again, I'm going to show you algorithms which, by gathering more examples, say more participants for your medical study, they can cope with arbitrarily high noise levels.
Is that what they do at the airport to see?
I didn't think about it, but that's a good application as well, I guess.
I take one slice from you and one from me.
Okay, and the third setting I'm going to discuss is learning with privacy preservation, which intuitively means that the learning process or outcome should reveal little information on any individual training example. And this has gained more and more attention in recent years because a lot of machine learning nowadays is done on data which is sensitive. So it can be medical records or financial transactions or internet navigation history, search keywords, and so on and so forth. And we don't want the learning process to reveal any sensitive data. So if we do the medical study and publish the results, we don't want someone smart to analyze these results and maybe use some side information and deduce that a particular John Doe in Boston has a certain type of lung cancer or maybe some other sensitive medical information. So to make this a bit more concrete and also put our work into context, I'd like to discuss a little bit what common privacy preservation protocols are out there for learning.
This last example is a bit confusing. So you're saying the learning process should not tell you this, but that's not, somehow seems to be different than saying that the data is noisy.
Well, okay, so here I'm not talking about noisy data. I'm just talking about the problem of learning where you don't want to reveal information on specific examples. So suppose that you use the data you gathered in your medical study to find some predictor, and you publish this predictor. So it turns out that certain types of predictors actually reveal a lot of information about particular examples in the training data. So if the data was sensitive, you don't want people, by analyzing the predictor, to find...
And what would be preferable in this case? That you don't publish the predictor, or you publish some other form of
Well,
data?
so you want... so I'm going to discuss it in the next slides, and I think it'll be clearer. Okay, so one important framework to learn with privacy preservation is the so-called sublinear queries framework. So the idea here is that the data custodian, who has the sensitive data, sets up a server, and people can submit queries to this server. And the queries are in the form of a function, and the server, what it does is that it takes this function, applies it on all objects, on all examples in the data, sums the result, and returns that as an answer, maybe with a little bit of noise added. And the idea is that this answer doesn't reveal too much about any particular object in the data. And it was shown that using this protocol, one can apply several learning algorithms, such as K-mean, PCA, perceptron, and so on, and also prove strong privacy-preserving properties. So these are the advantages, but there are also some disadvantages.
What do you mean, why is sublinear? Oh, the number of queries you can ask is sublinear.
Is very sublinear in the total number of examples you have. One disadvantage of this framework is that the data custodian actually has to spend some money and effort to set up this server, maybe hire some programmer to maintain it, etc. A more serious problem is the following. So who actually gets to submit queries to this server? So, you know, it can be respectable researchers like Adam here, who will use the data only for the good of science. I just took it from the internet. That I don't know. Well, in any case, other than people who will use this only for the good of science, there might be some evil hackers that try to reach this sensitive data. So I said this protocol, the server implements some functions submitted to it from the outside. But do we really want it to implement, say, some code which was submitted from the outside? Obviously, there are some potential security vulnerabilities here. Another problem is the following. So suppose we somehow solve this and only respectable people can access the server. And suppose that Adam comes along and he wants to implement, Adam, what's your favorite learning algorithm? SVM. Okay, so Adam wants to learn SVM, so he submits his query to the server, gets the answer, and learns his SVM. But now suppose that Mark comes along and he wants to learn something else. Say Mark wants to apply maybe a clustering algorithm on the data. So he submits his queries, gets the answers, and does clustering. Then Yael comes along and she wants to learn yet another thing. The point is that each time the server reveals a little bit of information on the sensitive data, and at some point the data would simply be burned out. The server won't be able to answer any more queries without compromising the privacy of the data too much. So maybe the first few people will get to use this protocol, but then no one would ever be able to use it ever again. Okay, the second setting is where the learning is actually done by the data custodian. So that received a lot of attention in recent years, and it was shown. Okay, so the idea here is that the data custodian applies some machine learning algorithm on the data, resulting in some predictor, and that predictor is published maybe with a little bit of noise. And it was shown that it's possible to learn linear predictors, including kernels, and I'll discuss later on what I mean by that, again with strong privacy-preserving properties, but again you also have similar disadvantages to the previous setting. So the data custodian has to implement a non-trivial algorithm, and you still have this problem that eventually the data will be burned out and you won't be able to use it ever again.
So wait, the data custodian doesn't output the algorithm?
No, he just outputs a predictor. Say the output, he outputs what the...
Does he output the predictor? Does he output the prediction of the predictor?
No, so he outputs the predictor, and anyone can use this predictor
as many times as he wants.
As many times as he wants. But the point is that maybe 10 years from now, someone will come up with this great new learning algorithm, and we won't be able to apply it to this data because the data is already burned out. It was already used both for SVM and clustering and a few other algorithms, and they won't be able to use it again.
Can I assume in all of this that Adam, Mark, and Yael cannot actually add to the data? Can they alter the data?
No. So in this model, we assume that the data is fixed, and you just want to learn from it. But you can make it more complicated if you want. Okay, so the framework in which we provide learning algorithms can be denoted as data sanitization. So the idea here is very simple. The data custodian takes the data, applies some distortion to it, and releases the result. And that's it. This is a very classic approach going back at least several decades to classical statistics, and it has been criticized in terms of its privacy-preserving properties. However, the learning algorithms that we derive are able to work with humongous distortion levels, enough to make this work with formal privacy-preserving guarantees. And at least compared to the previous frameworks, a potential advantage is First of all, it's very, very simple for the data custodian. He just has to do this simple calculation once. And once the data is published, it can be reused indefinitely. It will never be burned out because we just publish a declassified version of the data. And we show how to learn linear predictors, including kernels with formal guarantees. And again, we have this common theme that if the data set is large enough, if we have enough examples, it's OK to make the distortion level arbitrarily high and get arbitrarily high privacy level.
Of course, if that declassified thing later gets put together with something else, which is some data that was cleansed, which is on the same people, then you can have a problem.
Yeah, but I'll discuss it later, but we provide guarantees with respect to what is called differential privacy, which is, which has these guarantees, which it's like resistant even to side information and so on and so forth. So we give good privacy preservation guarantees here. OK, so now I need to show you that I can actually do everything I talked about. So now I'll start being a little bit more formal. So formally speaking, the setting is as follows. We assume that examples are drawn from some unknown distribution D. Each example, the instance x is some vector in Rd, and y is some real value. And for now, we're going to focus on the class of linear predictors, which is one of the most important classes in machine learning. So each linear predictor is parameterized by a vector w, and given an instance x, the prediction is simply the dot product of w and x. We also assume that we have a loss function, which measures the discrepancy between our prediction and the actual value. And we assume that this function is convex with respect to w to make everything I'm talking about here computationally feasible. And our goal in this setting is based on information-constrained access to a training example, to training samples. We want to learn a linear predictor with low risk, where the risk here is defined as the expected loss or expected discrepancy between our prediction and the actual target values.
So that's like, so least squares linear regression.
Yeah.
Least squares linear regression.
Yeah, depending on the loss function you take. Yeah. OK, so I said we want to find some predictor w whose risk is as small as possible. So if we knew this function, then it's not a problem. So for any bounded convex set C, we could apply, say, gradient descent, find the minimum of this function, end of story. The problem, of course, is that we don't know this function because it depends on this unknown distribution D. One way to deal with it is with the following very nice algorithm, which is called stochastic gradient descent, which works as follows. So it's a little bit similar to gradient descent, but it's also somewhat different. So it takes as input a training set drawn from the distribution, initializes w to 0, and then it goes over all training examples. And for each example, it does a gradient step with respect to that particular example. So again, if we knew this function, we could do gradient steps with respect to this function, but we don't know it. So instead, we do gradient steps with respect to a single example at a time. Eta t here is just the step size, which generally decreases with t. Then if we stepped outside of the set C, we just project back to it. And in the end, we return the average predictor over all rounds. Sorry? Yeah, this means the gradient.
So how can I take the gradient with 1 point?
Well, this is a function. You think of this as a function of w. And you take the gradient of this function for the particular x, t, y, t.
But I don't have the function, so I can't take the gradient.
You do know the function for a particular, so you do take one particular example in your training set. You do know x, t, and y, t. And then you know the loss.
No L. He's not
Less is
using.
small l is known. What is not known is this large L, which is the expectation of small l over d.
He's using something that he knows.
Yeah. So if you know x, t, y, t, then you can apply this algorithm.
He thought maybe you were trying to do that.
Oh,
Of course
no.
You don't know.
Just with what we know.
Right.
OK, so for this algorithm, it's possible to prove that if the gradients are bounded in a certain sense, and if C is a bounded set, then the expected risk of what the algorithm returns is at most the minimal risk in the set C, plus a term which goes to 0 with m, with the sample size. And if you want, you can also prove a stronger variant of this theorem where you actually have something which holds with high probability, not just in expectation, but I'll skip it for simplicity. Now, it turns out that instead of doing this algorithm, you can do something a little bit different. So suppose that for every fixed xt, yt, instead of doing a gradient step with respect to the example, you go and construct some random vector, z tilde t, which is only equal in expectation to the gradient. So the idea is that instead of doing this deterministic gradient step, you do something fuzzy, something random, which is only equal in expectation to the direction you actually want. And it turns out that even if you do this instead of the actual gradient steps, you can prove virtually the same theorem. So this is almost a folklore result which has been used several times both in the machine learning community. Sorry?
What is your O now? Because now your error is a random variable, right? So that is
You mean the expectation here, or?
No, but the z tilde t is chosen.
So you construct it in whatever way you want.
But it's the error in expectation with respect to z probability.
Yeah, so now it's
of
expectation with respect to the randomness of the zt's, in addition to the randomness of sampling your training sample.
So you see nothing about distribution.
I'm sorry?
You see nothing about distribution. It is only about the
Well, you do need the variance to be bounded, and you need it to be unbiased, but that's enough.
And
so
the constant of the big O is independent, is a fixed constant no matter which distribution.
Yeah, for any underlying data distribution. Again, as long as you have these minimal boundedness assumptions.
until you need the variance to be bounded with respect to the number of samples. I mean, okay.
Okay.
There's nothing hiding, that's the whole theorem, right?
Yeah, that's it. You don't need anything.
So the O is 4 or something. It doesn't depend on anything.
Right, that was just,
Yeah.
that was just
Or does it
Nadee's
depend on the
question.
dimension of your X space?
It doesn't depend on the dimension. It really only depends on what's written here. You just need the random vectors to have bounded variance. You just need the set C to be bounded, and it would still work. That's a nice thing about it. So as I began saying, so it has been used several times, both in the machine learning community, including by people sitting here, also in the optimization community, in works by Nemirovsky and so on. And this would be the key idea that we'll use to learn in an information-constrained setting. So the idea is that we won't have enough information on each example xt, yt to compute the gradient exactly. So we won't be able to do standard stochastic gradient descent. But we will be able to use the little information that we do have on each example in order to construct an estimate of this gradient, which would be noisy and random, but correct in expectation. And this theorem guarantees that once we create such an estimate, we can learn in this setting. So at some technical level, most of what I'm going to talk about is increasingly sophisticated ways to construct such unbiased estimates. Okay, so I'll begin with the simplest case, which is the attribute-efficient setting. So recall that in this setting, for any fixed xt, yt, you cannot see the vector xt. So you can think of this vector like as all the medical tests that you can do on each participant in your medical study. You can only choose to see a few entries of xt. You can do a few medical tests. And suppose that the loss function is just the squared loss, which is one of the most common losses in machine learning. So just the difference between the prediction and the actual value squared. By standard math, this is how the gradient looks like. So again, because we don't know each xt fully, we cannot compute this vector exactly. The xt is mostly unknown. But we can create an unbiased estimate of it based on querying a few entries. And this is the basic idea. So again, we want to estimate a vector which has this form. So the first, yes?
So what determines what our choices? Can we see yt in order to determine which coordinates of xt I want to see?
So you assume that you know yt, and you don't know xt, but you can query like the first, the third, and the fifth entry, say like up to 3.
And if yt happens to be large, I may do that. If Is that a
Well, you conceivably could do that. The algorithm we propose does not depend on the value of y, but you can do it. Actually, you can also generalize this a bit to assume that y is not completely known, but let's just focus on the x case for simplicity.
In your cancer,
so you need to know if someone has cancer to know what test
right.
he needs to.
No, I mean, you can do, so you have a lot of people that volunteer to your study. And when you do the follow-up study, you can ask each one whether he developed cancer or not. But in terms of the medical tests that you do, you know, the kind of attributes I talked about, like the genetic profile, CT scans, and so on, you can just do a small number of medical tests.
They don't depend.
they don't depend on
You do them
why.
before you know, your algorithm at least, you don't need to know whether they get cancer or not. You can just do the test
No, no.
first and then...
Yeah, you do the test first, and the algorithm doesn't depend on the value of y. Yeah. Okay.
Do you have to be able to question them, or what if sort of fate gives you random coordinates?
You mean in terms of the y value, or?
No. in the
He's
axis.
asking if you only get random,
Coordinates of xt.
random coordinates of
Oh,
xt.
okay. So, well, in our algorithm, we do need to have control on which entries we choose. I think you can also construct a variant where the entries are given randomly, but you'll need to assume that it's like uniformly random, or maybe you'll need to know the distribution or something like that. But what I'm discussing, you do need to control which entries you see, which is reasonable, say, when you conduct a medical test. You can choose to do these three tests, for instance. Okay, so the observations that we need is that, first of all, the vector x can be written as the uniform distribution over singletons, which depend just on a single entry of x at a time, dx1, dx2, till dxd. The second observation is that the inner product w times x can again be written as some weighted combination of elements where each element depends just on a single entry of x at a time. Okay, so how do we use these observations? So we do it as follows. So we're going to pick an index I uniformly at random from 1 to d, and we're going to pick j according to the distribution induced by the weights of our predictor, by the weights of w. We're going to query these two entries, xi and xj, and construct this vector, which is basically a random vector because I and j were chosen randomly. And based on the observations from the previous slide, the expectation of this thing, since xi and xj are independent, the expectation decomposes as follows, and we get that in expectation, this z equals exactly the gradient that we need. And now we can just plug it into stochastic gradient descent and learn. And notice that we use just 2 entries per example. However, if we want, we can also extend this to work with seeing k entries per example, where k is anything at least 2.
So you want to gain by seeing more, right?
So I want to gain by being able of, so I'll talk about it in the next slide, but the idea is that from each example, I'll only take, say, 2 entries. On the other hand, maybe I can get more examples, and this offsets the fact that you see just a little bit of each example.
Why do you need 2?
Well, technically I need 2 because I need the expectation of z to decompose. I want the expectation of this thing to be equal to the expectation of this times the expectation of this. I want these to be independent statistically. That's why I need at least 2.
You can get by with 1?
Because in information theory, if you do it long enough, then for each y I will have finally collected all the x coordinates. And
So I don't know in this case how to do it with 1. Actually, for the second setting, I'm going to show later that exactly one noisy copy, it's when I talk about noise in data. So with one noisy copy, it's impossible to learn. There seems to be something pretty fundamental going on here, that you need more than one noisy query per example in order to learn here. But I'll get into that a bit later. Okay, so formally, if we plug in this estimate into stochastic gradient descent, we get an algorithm with a guarantee which says that if the x's and y's are bounded, then the expected risk of what the algorithm returns is at most the lowest possible among all w's of bounded norm plus this term. And it's interesting to compare it to what you get if you use a full information algorithm, one that simply has access to the entire data. And then the bound has this form up to factors logarithmic in d. So you can see that here we have this extra factor d here, which is the price we pay for the fact that we see just one entry rather than all the entries. But on the other hand, you have here this parameter k, which gives you a trade-off. So remember that k is the number of entries you can see per example. So it's OK to take k to be very small and then see just a few entries per example. But on the other hand, it means that m, the total number of examples you see, has to be larger in order to achieve the same level of accuracy. So this is the trade-off that you need. So with this bound, no. However, it's possible to do a slightly more refined analysis, which does recover this bound.
The dependence on this doesn't seem dimensionally right for that reason. I would have expected a square root of d.
You mean like in terms of, because the k is inside the square root? Yeah, so first of all, it depends a bit. So this is a somewhat simplified form, which is sort of adapted to cases where k is small. Again, when k is large, like it's comparable to d, you can give something where the dependence between d and k is more linear. But so I do present it in a somewhat simplified form, but you can deal with it as well. OK. And just to give amusing examples, so we went and took the MNIST data set, which is a very well-known data set in machine learning. It's basically a collection of handwritten digits. And you can use it, say, for a binary classification. So say you want to train a predictor to distinguish between 3s and 5s. And if you go and use a standard algorithm to train a linear predictor, then you get a test error of around 1 to 1.5%. So for these algorithms, the data looks like the upper row here. Then we went and took our algorithm, and we forced it to use only 4 pixels per image. So there are 784 pixels here, and it can only observe 4. So for our algorithm, the data might look like the bottom row here. It obviously gets much, 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 much less information than the full information algorithms. And nevertheless, we achieve only a slightly higher test error of 3.5%.
But you did that more than once.
No.
No, on the full data set.
Once on the full data set. Only once on the full data set. You didn't make
Yeah.
passes.
How
Oh,
many
no.
3s and 5s do you have in your full data set?
I think on the order of 10,000. Something. It's a pretty large data set.
So
if
you
the data
just
set
have
is-
40,001 entries.
I'm sorry?
You have 40,000 entries which say 0 or 1.
4
Yeah.
per.
So for each example, you can see only 4 pixels. Yeah.
Just each
Right.
of the
So-
other ones. But for testing, you got to see all the pixels.
Yeah.
So just curious.
Yes.
And if this 3.5% is not something inherent, if your data set had been larger, you should be converging.
Yeah. I mean, we went and applied it on the same data set with the same number of examples, but according to the theory, if we've given enough examples, it would have converged to the same thing. I'm sorry? I don't remember what are the results. They were a little bit worse, but not something catastrophic. I think maybe 5% or something like that. It still works pretty well.
So when you can go into 1.5 when you increase the number?
Yeah, so, well, we didn't do we didn't try a lot of different pixel values. Like, we tried... No, but actually, our algorithm, I don't know how to implement it with one...
Oh, right. Right.
Well,
It has
I mean,
settings
you
too,
can...
you said. Remember these
You can sort of
guys
try to force it, but then you get these bias terms and you don't get something...
Why don't you make the second one up?
No, if
Well...
if you know the covariance matrix, isn't what you're trying to do somehow estimate the covariance matrix? Isn't why you need to...
Well, actually, you can do something a bit similar by estimating the covariance matrix. Actually, we have an analysis of such an algorithm, but the bounds are worse. And it's intuitively because you try to estimate an entire covariance matrix rather than just a gradient. Gradient is simpler, you get less variance, so. Okay. So moving to the second setting, where you have unknown noise. So remember the idea now is that you can't see xt, but you can only see independent noisy copies, x tilde t, and you only know that they equal xt in expectation, and there is some bounded variance to the noise here. Now, you didn't ask me, but you might wonder why I keep saying noisy copies rather than a single noisy copy. Well, actually, you did ask in a certain sense. So in this setting, I can formally prove that if the algorithm sees just a single noisy copy of the data, the setting simply becomes too hard. So if the noise distribution is really unknown, in the sense that an adversary may choose it, and under very, very mild conditions on the loss function, which is satisfied by just about any loss function used in practice, then it's impossible to be consistent. You won't be able to find the optimal predictor no matter how many examples you get.
So there are two distributions over here, the noise distribution and the distribution of data?
Yeah, exactly, yes. And here is the idea of the proof. So suppose the learner gets a lot of examples and it plots it here, and assume that the data, each xt is one-dimensional. So it's just a number. And assume that the y's are either, say, -2 or +3, doesn't really matter. And assume that all the examples labeled as -2, so the x's have this Gaussian distribution centered at -1, and the +3 examples have a Gaussian distribution centered at +1. And now the learner can think to itself, where did this data actually come from? How does the data distribution looks like before the noise? And he can think of at least two possible options. So one option is that the distribution it sees is really the data distribution and there was no noise added. But another option is that the real data distribution looks like the figure on the right here, and there was simply Gaussian noise added which smeared this into a mixture of two Gaussians. The crucial point here is that the optimal predictor for this is not the optimal predictor for this, and vice versa. But based on the data given to the learner, he simply cannot know in which setting he is. So it's information theoretically impossible for him to decide what is the optimal predictor here. So with one noisy copy, it's simply impossible. However, for linear predictors and square loss, two noisy copies are already enough to learn. And that's because we can use two noisy copies. So if I take the gradient of the loss function, plug in one noisy copy here and one noisy copy here, I get something which is random but correct in expectation. So I can apply stochastic gradient descent and learn. Unfortunately,
so in your counterexample, basically what you're saying is you can't tell the difference between the non-triviality of the distribution and noise.
Right.
And somehow just with two copies taking this gradient,
it's already enough.
It's already
intuitively,
enough to, and yeah.
So the intuition is that
intuitively, what is that gradient doing that's distinguishing these two?
Okay, so intuitively, the point is that you can think of it as the variance of the y equal +3 examples is different between here and here. With one point, you cannot estimate the variance, but once you have 2 points, you can see it. So in this case, you take two noisy copies and they'll be different. Sorry, here you take two noisy copies and they'll be exactly the same point, but here it will be different. So it,
don't you want to estimate the same thing either way? Don't you want to estimate the average of the two, which is like half?
No, because here you actually...
For the squared error.
No, so for the squared error, so here it's not, I'm not talking just about binary classification. I'm talking about, actually regressing to the values. So in this case, if I give you a point at +1 and ask you what its label, you'll say +3. Here, the optimal answer would be some weighted combination of +3 and -2. You'd probably say 1 or something. Okay. Okay, so this would work great with the squared loss, but notice that this is only because the squared loss has a very, very particular structure that we were able to exploit, and it won't work otherwise. Nevertheless, using more sophisticated techniques, we can actually derive algorithms which learn with unknown noise using general loss functions, which are smooth in a certain sense I'll discuss a bit later, and also not just linear predictors, but also nonlinear predictors using kernels. And since I know everyone here know all about kernels, here is a brief crash course. So kernels is really one of the most important and revolutionary developments in modern machine learning because it allows you to learn predictors which are very, very nonlinear while retaining the computational convenience of linear predictors. And the idea is that you take your instances and you map them with some feature mapping psi to some high-dimensional Hilbert space, some inner product space, and learn a linear predictor in that space. And I think the best way to illustrate it is visually. So just a minute. OK. So this was created by Udi Aroni in IBM Research. So suppose that you, just a second. OK. So suppose you have these dots in 2 dimensions. You have red dots here and blue dots inside a circle. And suppose you want to separate them. So you cannot do it with a linear classifier because a linear classifier always induces a straight line as the decision boundary. However, if you're willing to use kernels, such as what's called a polynomial kernel in this case, you can linearly separate them. And here's the idea. So here's the data in 2 dimensions. And now you map them, say, to 3 dimensions, as shown here. Now notice that in 3-dimensional space, the red dots and the blue dots are linearly separable by a plane. And after you learn this plane and you go back to your primal space and see how the decision boundary looks like, then your very linear plane in 3 dimensions turned into a nonlinear circle in 2 dimensions. So this is the basic idea. Now, at first glance, a problem with this might seem to be that, OK, so this was a simple example in 3 dimensions. But often people do this transformation to a Hilbert space with a huge number of dimensions or even infinite dimensions. And obviously, we cannot work efficiently with infinite objects. And then comes to our aid a very nice trick known as the kernel trick, which implies that in many cases, even if the space is infinite dimensional, you can efficiently compute inner products using a very simple function known as a kernel function, depending on the kernel you use. And you can use that in order to implicitly learn a linear predictor and apply it on new examples. So while this is a great and very nice tool, for our setting, it's also very, very problematic. Because this feature mapping psi can be very complex and nonlinear. In particular, if you take your noisy copy of the data and apply the feature mapping, it doesn't give you an unbiased estimate of the transformed example without the noise. So just naively applying stochastic gradient descent won't work here. Now, I won't have the time to go through our entire algorithm and how we tackle it, but I'll just give you like the core of the idea that we use. So forget for a minute everything I said about predictors and kernels and so on. I just want to discuss a small riddle in probability. So suppose that x is some real random variable. You don't know its distribution. You don't know its mean. But you can sample from the distribution of this random variable. And suppose you want to create an unbiased estimate of f of mu, where f is some function. So if f is linear, not a problem. Sample once and return f of x1. Expectation goes through. And you got an unbiased estimate. However, this doesn't work anymore when f is a nonlinear function, because the expectation doesn't go through. And worse, in many cases, I can actually prove to you that an unbiased estimate of f of mu based on some sample x1 to xn simply doesn't exist. There is no such estimator. Of course, I wouldn't have said all this if that was the end of the story, and indeed it isn't. So these impossibility results implicitly assume that the estimator is a function of some sample x1 to xn. However, what happens if we let n itself, the sample size itself, to be a random quantity? So here's the idea. So suppose that f is any continuous function you may want on some bounded interval. By a standard resulting analysis, one can construct a sequence of polynomials, a0, a1, etc., where an is an nth degree polynomial, which converges uniformly to the function f on this interval. Also assume that p0, p1, etc. is some distribution supported on all non-negative integers. And suppose that now you do the following. So you're going to pick n randomly according to this distribution, Pn, and then you're going to sample that many samples independently and return this complicated looking expression. So it turns out that the expectation of this thing equals exactly to f of mu. And yeah, so I'm showing it. So the proof is pretty straightforward. So, oh, okay.
Yeah, we just want to think about
Yeah,
what
so,
this is.
okay, so we have some function. We only know it's continuous.
Oh, so instead of taking x to the k, you're taking all these different.
So what you do is that you take a random number of samples according to Pn, and you construct this thing, and the expectation of this over the x size and over n, the sample size itself, equals exactly to f of mu.
And this is true for every p?
I'm sorry?
You're just taking independent samples so you can
Yeah.
make products of the thing.
Yeah.
And
Yeah.
this is true for every piece of I, which is positive for every I. Every sequence piece of I is.
Yes, but there's some restrictions which I'll discuss in 2 slides.
But basically, if it were a degree 4 polynomial, exactly, then you would only need 4 samples for sure.
Right. Yeah, you can't
Instead of
specialize
degree
this.
Polynomial, you wait till you get the right number of samples, and then you.
Yeah, but I mean, if it's a polynomial, then it's easy. The question what happens with general nonlinear functions. So the proof is actually quite straightforward. So this is the expression I showed you earlier. Now notice that the expectation of this thing over the x size, so each x size is equal to mu in expectation. They're independent, so you get a polynomial a n mu. Here it's the same thing with a of n minus 1, the n minus 1th degree polynomial. So the expectation of this entire thing is simply the expectation over n of this. When I write the expectation explicitly as the sum of Pn times this, the Pn's cancel out. And what I end up with is just an infinite telescopic series, which can be shown to be equal to the last term, the limit term f of mu minus the first term. And we can construct the polynomials however we want, so I could just assume this is 0, and I get f of mu.
Instead of a nonlinear function, you're taking sums of multilinear functions, which you're getting
Right.
from all your independent things,
Right.
so that your expectation just.
Right. But the degree is random. and
But the
that's-
degree has to, right, but you
Yeah.
can't do that with fixed degree.
Yeah. So it turns out that this technique was mentioned in an early 1960s paper from a statistical field called sequential estimation. According to Google Scholar, that paper received 4 citations, all in the same journal. The last one was 20 years ago, so at least to the best of my knowledge, and maybe someone in the audience can enlighten me on this, this is a very little known technique, which I think is a shame because it seems like a nice one which can be used for other purposes as well whenever you want to construct an unbiased estimate of some nonlinear function.
How did you find that paper?
Coincidence. I don't have. Well, we did think of a certain special case, and I had this feeling that there got to be something more general. And I went and Googled, and one particularly weird query brought this paper to the first page. Oh yeah, you're right. I should try it. Maybe it will work. Okay, so how does this technique relate to what we do? So the crucial observation here is that if the distribution Pn decays rapidly enough, then with very high probability, you'll need just a small number of samples. So if you think back of the setting where we can take independent noisy copies of the data and apply something similar to this, it means that we can find unbiased estimators of nonlinear functions of the data with essentially bounded number of samples per example. Unfortunately, you cannot take Pn to decay as rapidly as you want if you want say the variance of the estimator to have bounded norm. It has to depend somehow on the smoothness of the function f. But if, for example, f is an analytic function, it can be written as its Taylor expansion, then you can take Pn to decay exponentially with n, with the base being as large as you want. And basically, we use this technique to learn with noise using both large families of kernels and analytic loss functions. Yes?
I was going to ask a question.
Yeah.
Way back, but I just want to make sure I followed. So when you say learning with noise, you mean that for every X, I observe multiple copies of a Y is drawn with noise, so it's Y is error.
Yeah, so for each example, you're allowed to take a few independent noisy copies. So if you do a CT scan, a low-dose CT scan, then you are allowed to take multiple scans. And again, you can argue if the independence assumption is totally justified or not, but that's what we need in order.
Later, but I think if certainly the case with one X and two random copies, there's a proof known in the econ literature by Leon Wong that basically shows you can asymptotically recover the entire joint distribution of X and Y given this. And so if the setting is literally a measurement error situation, I have X plus 1 epsilon and then another epsilon, I get two different Ys, I can get the joint distribution of all errors.
Yeah, although in our case we don't try to learn the distribution, which can be, it's over Euclidean space, so you cannot learn it in general. We just try to find a good predictor.
Right, so that's a simple, but I guess what I'm saying is, if that were the setting, it wouldn't be surprising that you could find a functional, if I can recover the distribution asymptotically, right?
You're probably trying to find the mean.
Yeah,
and he's trying to do something more,
Yeah. But in our case, we do try to do something more complicated than just finding the mean, so you have to do something a bit more sophisticated. Okay, so just for those who like formal results, so here is one example. So suppose you take any dot product kernel you want. So this is a large family of kernels which are defined as a function of the actual standard inner product between x and x tag. So it can be, for instance, the polynomial kernel. This is what was used in the video you've seen before. And it's possible to show that for any q you want, I can construct an efficient algorithm which, given noisy access to m examples, queries each example 1 plus order of 1 over q times with high probability, and returns w with close to optimal risk over all predictors of a bounded norm. So first of all, notice that q is essentially a user-defined parameter. If I take q to be large enough, then I can learn, even if I query each example, a number which is very, very close to 1. On the other hand, I showed you earlier that with exactly one query, for example, the setting becomes impossible. But if you allow me just a little bit more, just querying a little bit more with arbitrarily small probability, then the setting already becomes learnable. However, you have a trade-off here. So you can take q to be very large, but then the bound that you get here gets worse. So to offset it, you'll need more examples. You'll need m to be larger in order to achieve the same level of accuracy. So basically, q gives you this trade-off between how much data you get per example versus how many examples you get overall. Okay, so in that technique, we assume that the noise is unknown, and we use this random number of noisy copies in order to learn. However, one might ask, what if the noise distribution is in fact known? Maybe it's even chosen by us. Can we do better? And the answer is basically affirmative, with the one possible application being learning with privacy preservation. So remember that when I talked about privacy preservation, I talked about sanitizing the data, inserting some distortion into the data, and then learning based on that. And in particular, we're going to focus on a very simple sanitization procedure. So what you do is that you take each example with, say, entries bounded by 1, and then you publish 2 noisy copies of the data, where the noise is simply a Gaussian random vector with very large variance. So you should think of S here as being really, really large, like several dozens or even hundreds, enough to make a recovery of the original data virtually impossible. Now, this is not really a talk about privacy preservation, and I think I'm starting to get a bit short on time, so I won't go into all the details, but basically if the variance is large enough, you can prove strong privacy preserving guarantees. So you can prove differential privacy, which is like this very popular notion of privacy initiated by Dwork from MSR. Even for slightly smaller noise levels, you can prove a slightly relaxed notion of differential privacy. So again, the important thing here is that if you put in enough noise here, you indeed can preserve the privacy of the data. So again, if you're talking about linear kernels and the squared loss, then you can use the same technique as before to learn with just 2 noisy copies of the data. You just plug in the two noisy copies here. You got an unbiased estimate of the gradient, so you can learn. But as before, we can ask, but before that, so formally, the theorem that you get is as follows, where S now gives you this trade-off. So when S is large, you'll need more examples to achieve the same predictor accuracy. But on the other hand, you can guarantee more privacy because you injected more noise into the data. And as in the previous setting, we can ask what happens if we don't want to learn linear kernels. So suppose we take Gaussian kernels, which is maybe the most popular kernel in use today. So the inner product with this kernel looks like this function, where sigma squared is some user-defined parameter. And this is a very nonlinear kernel. In particular, naively doing gradient descent won't work. Just plugging in the noisy copies into the gradient won't give you an unbiased estimate of the gradient. Now, one way to deal with it is with the general noise technique where you had a random number of queries per example. But in this setting, it's not really a good thing to do because with some positive probability, maybe we'll need a lot of queries. Maybe we'll need to go back to the data custodian and ask for more copies. It compromises the privacy of the data. Can we do better? Can we really use just two copies even when we do Gaussian kernels? And it turns out that you can. And I won't have the time to go over all the details. But again, just this very, very rough high-level idea. So what we do is that we go and construct a different mathematical space, a different Hilbert space with a different feature mapping. And we construct it in such a way that it has this funny property that if you do standard gradient descent in that space with your two noisy copies of the data, it implicitly corresponds in expectation to doing gradient descent with respect to the clean and unperturbed examples. And I'd be glad to discuss the technical details offline if anyone is interested. Intuitively, this is possible because there's this very special coupling between Gaussian kernels and Gaussian noise. It's not a coincidence they have the same name. And in some sense, if you convolve a Gaussian kernel with a Gaussian noise, the result still looks like a kernel, but a different one that belongs to a different space. And we use this idea in order to learn with just two noisy copies of each example.
So you couldn't do this with something other than a Gaussian kernel?
Well, actually, I think it is possible, but it would get more complicated. So you need, so it's something we still need to look into more deeply, but basically, the only thing you need is to construct a space where convolving inner products in that space with your noise gives you what you want. So Gaussian is easy basically because a convolution of a Gaussian and a Gaussian is still Gaussian.
But if you had like stable distributions where you could add up exponents or something in some nice way.
Yeah, so I think it is possible to generalize it, but we still haven't looked too much into it. We focus just on the Gaussian kernel case.
Noise is under your control. You can, or rather,
yes,
you can add as much noise as you want, but it's still two samples.
Yes, and the algorithm, unlike the previous setting, knows that it's Gaussian distribution and knows its variance. Okay, and again, it's possible to prove a formal result. I won't go over all the technical details, but again, you have this nice thing where a higher S provides more privacy at the cost of requiring more data. Okay, so to summarize, in the standard learning model, this idea of having more examples is usually seen as a way to get you better predictor accuracy, getting something closer to the optimal predictor. In this talk, I talked about more examples, but from a different angle, where more examples actually makes up for individual examples of arbitrarily low quality or arbitrarily little information on each individual example. And I talked about 3 different settings. And I think that on a technical level, these are also nice illustrations of the power of randomness, which is a very general phenomenon in computer science. So here, in the attribute-efficient case, we were able to learn by constructing random vectors. In this case, we were able to learn by constructing random functions. And in this case, we constructed a different mathematical space where randomness in that space corresponded to doing the right thing in the original space. And just to conclude, so this is the list of my publications, and I talked today about these 3 papers here marked in red, but I'd just like to take 2 minutes to explain the common theme in my other work as well. So machine learning is a very broad field, has also lots of connections to other fields as well, and there are all kinds of standard ways to taxonomize it. Unfortunately, I cannot really put all my work into one neat compartment. So, for instance, one very rough high-level partition is between supervised learning and unsupervised learning. As you can see, I did work in both. So blue is supervised, red is unsupervised, and green is stuff which sort of applies to both or discusses strictly more general settings. You can talk about theory versus algorithms, these pure what is learnable type of questions versus more applied how to learn in some setting type of questions, and I'm interested in both. You can talk about statistical learning versus adversarial learning, where the data comes from some adversary or corrupted by an adversary. And again, I did work on both. So the common theme of my work is a little bit different. So I guess you can put in the center here a circle which represents settings with known formal guarantees. These are settings that we basically understand, which correspond to the standard models, where the data that you get for training is the same as the data you're tested on, and so on and so forth. Now, there are lots of important and interesting research questions inside this circle here. How can we improve our algorithms? How can we understand better what they do, etc.? But if I need to mark here where most of my research interest lies in, I'd probably put something like this, this green band outside the blue circle. So I'm interested in settings which are hard, which are not well understood, which go beyond our standard models or require non-standard techniques in order to tackle them, not necessarily in one specific subfield of machine learning, with the overall goal of making this blue circle just a little bit larger. So you've seen a few examples in my talk today, but I also worked in all kinds of other directions, which I'd be glad to discuss offline. So I'm still very, very far from covering this entire perimeter, but I did work on more than one patch, and I hope to cover at least a few more during my postdoc. So that's it. Thank you very much.